Oh, how good are you? Like this I'm really I want after the like as many people as I've never been we talked about like everything too, like all the things that are like I don't even know any of these people. Yes. I don't have a lot to say. Like that's so I don't think it's like put that. You guys yeah, I think I don't know. I don't know. If it was up to me, like nobody else, like I should have like 130 it's be like.
Now that we're done with it.
Like one, yeah.
Okay, folks, let me start this thing now. you cold?
I
haven't been outside.
It feels hot.
Yeah.
It's 70. Is it? It's just overcast.
It's like 60.
It's
It's-
I haven't been outside this building since I walked in at 6:45 this morning. So, and yes, I'm very cold for some reason. Maybe because I haven't been outside this building. Oh, that happens though for me. I come in and I never leave. Okay. So what we're going to be doing today is I am going to pick up where I left off this morning. I am going to continue with our discussion of covalent molecules. The first one I'll do is going to be hydrogen when mixed with groups 15 through 17. And then I will move on to alkanes, and then we will discuss binary covalent molecules. Depending upon the time frames, either there or shortly thereafter, we'll take a short break. Then we'll come back and we'll do acids. And finally, we'll get into a little bit on formula mass and molar mass. So that is the plan for today. So I am glad to say that this is now up and running. It wasn't earlier, so I wasn't able to record. So I will be recording for this class period, and this will be the one that I'll be uploading. So let's go ahead and get into the information. So we've been talking about covalent molecules. Covalent molecules contain a covalent bond, which arises through the sharing of electrons between two atomic nuclei. We talked about the diatomic elements this morning. Basically, they are elements that always, when found in nature, come in pairs. And so you had two ways to remember them, either through Brinkelhoff or through the fact that there are 7 of them and they form a nice number 7 on the periodic table. And then you got to add hydrogen to it. Now what we're going to talk about is we're going to talk about hydrogen combined with group 15 through 17 nonmetals and metalloids. And folks, what I'm about to discuss is a precursor for binary acids, which we'll be discussing a little bit later on. So let's talk about the formula for these compounds. The number of hydrogens that combine with the groups 15 through 17 nonmetal or metalloids is equivalent to the number required or the number, required if the non-metal or metalloid were an anion. Let me just illustrate what I mean by this. So for example, we know that nitrogen, when it is an anion, has a 3- charge. What we're going to do is the number of hydrogens that we're going to add is going to be equivalent to that 3 in the 3- charge. So the formula for this compound with nitrogen would be H3N. Phosphorus, again, because it has that 3- charge, it would form a formula of H3P, as would arsenic. Now, oxygen, on the other hand, it has a 2- charge, and so when it combines with hydrogen, it will do so in a 2-to-1 ratio, as will sulfur, selenium, and tellurium. Finally, your group 17 nonmetals, they always form a -1 charge. So when hydrogen combines with them, they do so in a 1-to-1 ratio. Now, the reason for this, as we will see when we do start to make acids, is because when it's in its acidic form, it will take on the charge of the anion, and each hydrogen will take on a +1 charge. Now, to name these, because they always have the exact same formula, or because the ratio is set for these compounds, you name the hydrogen followed by the name of the second element, with the ending IDE. So this first one is hydrogen nitride. I'm naming the hydrogen and then I'm following it with the second element with the ending IDE. The next one is hydrogen phosphide. And hydrogen arsenide. Now, the story I'm telling where you use hydrogen followed by the second name is going to be a true story except for the next compound. The next compound is known worldwide by a very specific name. And so instead of using its IUPAC naming or using this naming form that I'm giving you, we're simply going to call this one water. So again, instead of using the IUPAC naming or this naming method that I'm giving you, we're simply calling H2O water because it is known worldwide as water. Maybe with different spellings, but it's still water. Okay, so continuing on in this story, the next one would be hydrogen sulfide. Hydrogen selenide. Hydrogen telluride. And then you get into the next grouping. So hydrogen fluoride. Hydrogen chloride. Hydrogen bromide. Hydrogen iodide. And finally, hydrogen acetatide. Now, this may be a weird naming method for you. Like I said, it's not a pure IUPAC naming style but it is a valid naming style due to the fact that it always occurs in the exact same ratio. So we don't have to be specific as to the number of hydrogens compared to the number of the other element. It also may seem a little bizarre because of the fact that I am using, like for HCl, hydrogen chloride. Well, again, this comes back to the fact that this is a precursor for acids. And as a precursor for acids, for the most part, these have the state of matter of a gas when we're talking in this format. It doesn't become an acid, which is the more common way most people are used to seeing HCl listed. It doesn't become an acid until we dissolve it into water. So that's why it's a precursor to an acid. Okay. Any questions over hydrogen in group 15 through 17? Because that's all there is to it. If not, then we'll move on to our third type of covalent molecule. And technically, it's not just a covalent molecule. It is our first organic compound. And that is the alkanes. Now, not every class spends any time on alkanes when naming, but I feel like it's important for you to at least learn the basics of how to name an alkane. Because number one, we will talk about combustion reactions. Well, alkanes are usually one of the reactants. We'll talk about various things related to them, like balancing chemical equations. It'll come up. Well, we'll see an alkane, and I feel like it's important when you are learning to chemistry to go ahead and spend a few minutes, because it doesn't take a long time. I feel like it's important to start learning these alkanes. Trying not to cough. So I go ahead and spend a few minutes on the alkanes, but not every class does. So an alkane is an organic compound. It is the first organic compound you're going to encounter if you take organic chemistry. Because it is the simplest of all organic compounds. Alkanes are the simplest organic compound they contain carbon and hydrogen only, and they are the result of all single bonds within the compound. For their formula, they have the generic formula of C subscript N H subscript 2N plus 2, where N is the number of carbon atoms. I'm going to leave a little bit of space, and I'm suggesting you leave a couple of lines because we'll come back and talk about how to name them. And that way you have all the instructions. But we're going to go ahead and I want to pull up and do the actual formulas. So if I have one carbon, then it's C1. My H would be 2 times 1 plus 2. So in other words, it would be CH4. 2 carbons, it would be C2. H would be 2 times 2 plus 2, or in other words, it's C2H6. 3 carbons, C3H 2 times 3 plus 2, or in other words, C3H8. 4 carbons, It'd be C4H2 times 4 plus 2, or C4H10, and hopefully you got the gist. So the next one would be C5H12, C6H14, C7H16, C8H18, C9H20, C10H22. Now, technically, it does not end at 10. And technically, once you get to 4 carbons, you can arrange this in a variety of ways. Their structure can be arranged differently. You can have multiple that have the C4H10. But the entire point about the alkane minimum at the very basic is that its formula is CnH2n plus 2, and it's nothing but single bonds. That's the key to alkanes. Now, again, I want you to know these because I feel like it's important in part because you do encounter these on occasion. At least some of them. The very first one is called methane. Methane is a gas given off by cows and other creatures. Methane is a greenhouse gas, just like carbon dioxide is. The second one in line is called ethane. If I can spell today, I would appreciate it. The third in line is the gas that is required to, or is used to heat homes. It is propane. The fourth in line is the gas that is found in lighter fluid. It is butane. The fifth is pentane. The sixth is hexane. The seventh is heptane. The eighth is the one that is used for gasoline. It's octane. The ninth is nonane. And the 10th is decane. Now I'm going to go back to the naming. What do you notice about the naming? One is they all end in ane. That's appropriate that they would all end in ane because so does the word alkane. In fact, the ending is extremely important. Just like earlier when I was saying that the ending of the anion helps us determine what we're working with. The ending ane tells us we're dealing with an alkane. So if you go out there and you look at the back of a material and see a label, and it has, if you come across anything that says ane at the end, that means that it's an alkane. Okay, now there's one other thing though that can be noticed about the names, but not really until you get to the fifth one and down. What can you tell me about the fifth one down and down, I should say? Fifth, sixth, seventh, eighth, and ninth, 10th. It's just like shapes. So starting with the fifth carbon, or starting with the fifth alkane, the prefix is equivalent to that of its geometric shape. So in Washington, D.C., we have a pentagon, which is a 5-sided structure. Our 5-carbon alkane is called pentane. Every time you're driving along and you hit a stop sign, you're looking at an octagon. Our 8-carbon chain is called an octane. Now the rest, I would suggest you just memorize MEPB, methacprobute. Because there is no, I can't give you an easy way to memorize the first 4. So what are the memory takeaways on this? The memory takeaways are alkanes have a generic formula. So as long as you know the number of carbons, you can figure out the rest of the story. They all end in ANE, just like the name of the group, alkanes. And starting with the 5th carbon on, they are the prefix is the same as the geometric shape for that number. And then finally, methacprobute. That's your first 4. Those are the key takeaways for alkanes. If you know those, you can figure it out. Any questions about alkanes? Then we move on to the 3rd type. We move on to binary covalent molecules. I should say the 3rd type this afternoon, the 4th type overall. Okay, so your binary covalent molecules. The first piece is found in the prefix binary, bi. Basically, it is a molecule that consists of 2 metalloids and or nonmetals. Covalent molecules because, or I should say with covalent molecules, because they arise through the sharing of electrons, the same two elements can combine in multiple ratios. This is very different than what we've talked about up until the alkanes. We talked about ionic compounds. Ionic compounds of the same two elements can only form in a certain ratio. It's all based on the charge of the cation and the charge of the anion. We got to diatomic elements. They can combine and they're always in a pair. We got to hydrogen with group 15 through 17. It's always in a specific ratio. But when we got to alkanes, what we noticed is that carbon and hydrogen, they were able to, I gave you only 10 of the possibilities. There's more possibilities, a lot more possibilities. This is because in covalent molecules, we're dealing with the sharing of electrons. And so the number of possibilities grows exponentially. That causes us problems. Well, it doesn't, but from a initial standpoint, from learning this, that causes problems. Because we can't do what we did with hydrogen in group 15 through 17. We can't just call out the first element and the second element. Because no two compounds can have the exact same name. No two compounds have the exact same name. So we can't just call out the first element and the second element. For example, I would not want to call both of these carbon oxide. Because they're not. Calling both of these carbon oxide is a bad idea. Well, that's real good for that. The reason it's a bad idea is because one of these will replace the oxygen in your blood to kill you. I'm not saying the other one won't kill you. There is that possibility, but it's much tougher because it doesn't actually go into your bloodstream. One of these, we actually are, more and more homes come with a detector for. Where's the other one? No. One of these, though, is a greenhouse gas, while the other one's not so much. So I wouldn't want to mix these two up because there's a lot of differences between them. The first one of these is carbon monoxide. which is the one that will replace the oxygen in your bloodstream. The second one of these is carbon dioxide, which, like I said, can kill you. I mean, you can suffocate if all you've got around you is carbon dioxide. But it's less likely to kill you unless somebody is intentionally trying to kill you or you're intentionally trying to kill yourself, then please don't do that. It has to be intentional. The other one you don't even know happens.
Can't it, like, boil out of your blood if you rise too fast to die? Think of something else.
That one I don't have the answer to. Let's see, a change it, so let me think about that one and I'll answer you. Because I can think about it from a term, and it's gonna be a change in pressure is what's gonna go on. So I'll have to think about how fast. And it could expand quite a bit, yes. Okay. So let's get back to the binary covalent molecules. And let's talk about, normally I talk formula first, but this time we're going to talk naming first. So we have to differentiate. No two names will be the same. And you have to differentiate between compounds containing the same two elements. The way we do so is a prefix system. Is used to identify how many of each element is present in a compound. You've actually already been introduced to most of the prefix system, with the exception of the first four. When you have one, it's called mono. Now, there is a note to be made about mono. And that is mono is only used on the second element. In a compound. The prefix for two is di. The prefix for three is tri. The prefix for four is tetra. The prefix for five. This is where we get into the same prefix system now as we were using for our alkanes. The prefix for five is penta, six, hexa, 7 is hepta. 8 is octa. 9 is nona. 10 is deca. Now, there is one more note to be made. And that is if the second element, or if the element, not the second, if the element begins with an A or an O, then the A of the prefix is left off of the prefix. So we're going to look at a couple of examples. I've already done carbon monoxide and carbon dioxide, so let's look at SO3. We have 1 sulfur and 3 oxygens. The prefix for 1 is mono, but mono is never used for the first element. And then we have sulfur. The prefix for 3 is tri. And then you have oxide. So putting it together, this compound is called sulfur trioxide. N2O5. According to the formula, we have 2 nitrogens and we have 5 oxygens. The prefix for 2 is di. And then you have your nitrogen. The prefix for 5 is penta. And then you have the oxygen as oxide. So this is dinitrogen pentoxide. Here is one of those examples where I omitted the A on the prefix because the element started with an A or an O. In other words, folks, it's straightforward in naming these binary covalent molecules. I think, and it's also straightforward to get the formula, because if I go tetra phosphorus decoxide, let's think about this. We're going to take each one of these and we're going to pull it out. So tetra means 4. Phosphorus, well, that's P. Dec, whoops, put it in the wrong spot. Dec means 10. And oxide means O. So the formula is P4O10. Binary covalent molecules are fairly straightforward. Questions?
They would not be simplified at all.
No, I'm glad you asked that. Covalent molecule formulas do not get simplified. And that's because, again, when you talk about covalent molecules, because they arise through the sharing of electrons, we can make a ton of different variations, and we have to be very specific. So no, covalent molecules don't get simplified, only ionic ones do. Okay, so we're going to get a little bit into acids, and then before we'll be able to take our break. Acids. Acids, we will be using the Arrhenius. And or the Bronsted-Lowry. Definition of an acid. Which is that it is going to be a proton H plus donor. For the formula, there are some key pieces. The first is that frequently, not always, but frequently, the acidic hydrogen or hydrogens is listed first. The second is again the same as we found for the hydrogen with group 15, 16, and 17, is that the number of hydrogens equals the magnitude, the numerical value of the anion charge. And the last key factor for our purposes, again, this is for our purposes, is that the compound will be an acid only once it is dissolved in water. And so it has the state of matter of aqueous, which will represent with AQ. So we will include AQ into the formula. Now, I will warn you that when you come to active, it doesn't ask you to include AQ in the formula. So on active, you won't be asked to include AQ in the formula, but for my purposes in class, we will include the AQ. So Cl minus. This is chloride. We've already talked about if it's with HCl in the gas form, this is hydrogen chloride. But when hydrogen chloride is added to water, then we get our acid of HCl, aqueous. Sulfate is SO4 2-. So to get to the formula of our acid, because it has a charge of 2 to get to our formula, that means we're going to need 2 hydrogens. And we're going to add aqueous. NO2-. It has basically a -1 charge. So we will need to add 1 hydrogen to it, and then aqueous. Okay. Before we get into naming, I'm seeing a little bit of glaze over. So we're going to take a 15-minute break. So you have until 3:50 to come back. That way, if you need a snack or drinks, you have time to run and get it. So again, 3:50, we come back and we'll continue with the naming of acids. And then we're going to practice it like it's really going to be, which is all mixed up. It's not that far to Starbucks, but Starbucks line, you never know how long it's going to take.
Sometimes.
I mean, admittedly, we're in the middle of a class, so it wouldn't probably be as bad as it would be in between classes. And if you had your own K-cup, all you would have to do is go next door to our ACS room. Well, from now on, if y'all have a K-cup for lab and your own cup, you can run to our ACS lounge. We have our American Chemical Society students take care of the lounge, and we have a what I call Keurig Light, but it can make iced coffee or it can make regular coffee. It makes cocoa too.
Actually, look at that.
I have a bunch of K-cups that are cocoa.
That does sound good.
It's right around the corner. Oh. Yes.
Look it up. My question.
Now that I can see. Because nitrogen, I mean, makes up 78% of the air you breathe in. It's free. So I could see it. It's also weighs less than carbon dioxide. Because carbon dioxide will weigh 44 grams per mole, whereas nitrogen's only 28. So I could see it very much being affected by the pressure. So I could see it boiling out. But I didn't know definitively without. I wasn't gonna answer wrong. So, I mean, any gas could boil out. And I know that as you go from, if you've got a certain amount in you, and as you go to lower and lower pressures, it does tend to try to come out.
Yeah.
So like in a balloon, as you go up into the atmosphere with a balloon, it's gonna be expanding until it breaks. Well, our body has enough holes in it that as you come up, it's gonna come out. So. But that is cool to know.
That's interesting, because, I think even going somewhere around 400 feet down, it's enough of a pressure difference that if you rise,
Excuse me.
Yeah, you can blow up your lungs.
yeah, pretty much.
Oh, goodness. That's what he said. I'm just sitting here. I'm an old soul too, but I've actually got the age to go with the old soul, so I'm in real trouble. I'm no longer a slave. Ugh.
I literally put on the bottom. I was confused. This is the best you're getting. No, she has a little area. Place your thoughts since last class.
I'm scared. It's a direct quote from Oliver himself. Direct quote. Correct. Oliver himself.
I don't even know what I'm writing
You should.
Was. Let's just.
Okay, I don't know how to spend it. Cause I didn't really read most of it. It made no sense. That's what it is. Or in the first like 3 pages. Okay, read what I have. Figure out, I can't just, I know it needs more like explanation. I just don't know. Here's the bullshit. I think. Hold on. Right here. Yeah. No question, it just, it's there. Is it too close? I put too close. Oh. That's why I was confused. Yeah. That was my error. I need to do that too.
It's probably illegible. I'm writing everything down, but it's. I don't know if it's. I am ignorant. Just go straight to the bill. Wow.
You didn't get that? Yes.
Yes.
It's sufficient. Just add a measure of the sense of explanation. No, but I feel like it's really fun. Alex really likes to return my words to me and make me do it. So I feel like one more quote or one more little sentence will keep it from doing it.
She drinks LaCroix and those are even worse.
No, I think it's by the these basically, it's like regular soda. So it's sweetened with Splenda, anything like that.
Just see.
It's the reading.
Doesn't just reflect that, like, not feeding your whole head. That's exactly what she does.
Thanks.
Yes.
Yeah, so
You could just you didn't have my.
no artificial colors.
Is it good?
So they're looking forward to it. I know.
I saw that actually. No, I don't think. It's like,
They're like moving.
It's no.
This assignment is awesome.
Which is good, which is why.
For honor. Not for chemistry. So don't worry.
I was like, I don't think I read that.
Chemistry is the only
Can't
class
even see
that
perfect.
is not making me want to.
So I was not that up.
I'll do that.
Not even.
I love my ass stitching. Oh, I love my super works.
Well, good.
I'll do this. In your ace cave. I love artificial sweeteners.
Yes, please.
It's terrible.
Can you just tell me, like, just like
It's all-
I will fully like compliment you.
That's because it's a big specific.
Oh, we only have 3 minutes.
What about sugar?
And I'm not stupid today.
What's your favorite artificial sweetener? Dr. Herman? Stevia?
That's what I was saying.
See, aspartame has my heart. Love the super low.
Aspartame is just terrible for you.
But you actually, stevia is a alcohol, a sugar.
Is it really?
This game is so bad.
How bad? Sorry.
Anytime you see the ending OL, if you look at the back and it says something with like an OL,
This is stevia leaf extract. That's also.
but anything with an OL is an alcohol. It's organic alcohol.
Okay, wait,
So sorbitol and stuff
do
like
you think I
that.
need more on explanation? Because I
Our
feel like
artificial
explain
sweeteners
it in
is
the
bad.
total
It's
paragraph.
like, some people say they're bad, some people say they're okay. From what I've read,
This is, I've
that
decided.
in
I
moderation,
don't care.
In moderation,
They're not
they're fine.
because I know they cause cancer in rats, but there was one study,
Yes.
the,
Disruptive.
but,
I'll put it this
the
way,
amount that they had was
The
the equivalent to like 20 cans a day for a human being. Like,
I will put it this way, our vitamin.
That's another issue.
Read those
Yes.
articles too,
But I
but
understand.
they have not gotten on with their,
What we're
like,
like.
their aspartame.
No.
If you give me numbers, I can fill it in.
It's still better for you. That's what I mean.
Actually, no, it's not.
Yes. Basically,
Not
look at
for
the best
weight.
ones, but you're probably just like,
But for other, like,
you have like max
metabolic function, other like just.
Some
of it, yeah.
Oh,
But it's actually, they actually say that, for those people that are trying to lose weight, it's actually easier to maintain organically.
Really?
From what I've heard, like, can cause you to get more space.
I'm like vibrating.
It could seem a crazy argument, but I don't know how else it would. Because, I mean,
Because you think you're getting 0 calories
And then it
and
allows you.
0
I have
and
my life.
other stuff that, there's
I
other
made
stuff
that
in
one.
there
I made it
But
like
it's
a-
still-
bad for you.
That's the first step.
It causes weight gain.
The dilated.
It's 0 sugar. It's not 0
See,
calories.
that's
it's
what
still
I'm
like,
saying,
what,
right?
5 calories?
This stuff was 0 calories.
It's-
What do they let it
it's
go?
D.
Plus or minus 5 or something?
I don't know.
I think it's about 5 calories there.
You don't get like 2 calories.
Okay, it's that time.
That's so much substantial weight gain.
No, it's- That's not it, that's the one thing.
Okay. So now what we're gonna do is we're gonna get into the names. And with names, if you don't know your ions, specifically the ending of those ions, you cannot name acids. Because the name then is based off of the suffix for the anion. And here's where I'm gonna go color happy. Again. Me and my color happy. If the anion ends in IDE, then the acid will have the prefix hydro, followed by the root of the anion, followed by ic acid. And I used to teach binary acids and oxy acids separately, but I realized they can be treated the exact same. So if your anion ends in ATE, I think my then it's gonna be the root followed by ic acid. And if the anion ends in ITE, it's gonna be the root followed by us acid. So earlier, I gave you Cl minus, which I said was chloride. In other words, it has the IDE. So HCl aqueous is going to have the prefix hydro. It's going to have the root of the anion chlor, and then it's going to come up with ic acid. So that's hydrochloric acid. Earlier, I said, okay, we have SO4 2 minus, which is sulfate. So the formula of the acid was H2SO4 aqueous. Because it ends in ATE, that means it's going to be sulfur, and then it's going to get the ending. Come on, be nice. Ic acid. So that is sulfuric acid. And finally, I gave you HNO2. We had NO2 minus. NO2 minus is the iron nitrite. So since it ends in ITE, it's going to end, the acid will end in us acid, and this will be nitrous acid. So really, on the acid front, what do you need to have memorized? This factor is huge. And then as far as the rest of it, that. The number of hydrogens is equal to the charge, and then you always put the aqueous for my purposes after it. Questions? I think some practice is in order. A lot like you might see on a test, right? Okay. So on my test, everything gets mixed up. So before I actually get into the practice, because I can't remember if I've mentioned this in this class or in the other class. If you look at this week's folder under the optional homework, one of the things that you're going to see is you're going to see a optional homework that focuses on creating the formula of an ionic compound all by its little lonesome. You'll see one that's creating the name of the ionic compound all by its little lonesome. And then you're going to see one that is covalent molecules and acids all by its little lonesome. Those three is is where I would start. I would go ahead and do those three. Because what it's gonna do is hopefully by you doing those three, it's going to give you that, repetitiveness that helps you. But that isn't what the test is gonna look like. The test is gonna mix up everybody. So since the test is gonna mix up everybody, you wanna see it more like what the test is gonna be. And that's where the other two documents come into play. There's one that's mixed formulas to names and one that's mixed names to formulas. Now, they're quite lengthy by themselves. And this is how I would really approach things. Once you've got that repetitiveness going on so that hopefully it's becoming more and more ingrained, do the mixed ones. But here's how I would do it. I would cut them in half. I would do half of it at the beginning. And then go and check the answer key. If you get it wrong, just mark it. Do not change your answer though. Just mark it and come to me. Let me see your answer. Let me see if maybe there's some sort of trend going on where you're mixing something up and it's mixed up. And so maybe I can find a trend in what you're missing. But if you've changed your answers, I won't be able to see that. I'll just know which ones you got wrong, but I won't know why. So do the mixed sheet and then come see me. And let me see if I can figure out what trend is missing in your brain. And maybe we can identify it. Then that would save the other half of that mixed one for studying for the test. Does that make sense? So in other words, using that resource. And then of course there's all the Quizlets. So let's look at how it will be listed. There will be 2 columns. In column number 1, I'll give you the formulas and ask you for the names. Column number 2, I'll give you the names and ask you for the formulas. So now I just got to make up stuff. I know, I'm getting low. right today. Okay, that's probably enough. And y'all can fucking work together. SN. Element number 50. First thing I would do, folks, is figure out, is it an acid, is it a covalent, or is it a ionic? Acid means it's gonna either say acid or have aqueous. Ionic means that it's gonna have a metal or it's gonna have the polyatomic ion ammonia. That kind of gets you into these categories that I was talking about earlier. And it may help you. Bromine, we're just talking about the element with Br, but in nature it's always found in the and it's different than bromide, which uses charge. I know,
I've heard the 7 before.
You heard what? Oh, the
The 7 and then the hydrogen. Yes, I got essence. This is all.
Yes.
What's the first one? No.
I means what? There's I, eight, and I.
It's.
I tells you what? No,
What is it?
diatomic is just their element name.
Is it like that green? I mean,
Oid means that it's an anion of an element with 3 exceptions.
Yeah.
So not quite. You had the oid.
oh,
You gotta know the oid, the ite, and the eight.
so is it?
So it's just an anion of an element.
That's what they're doing all these. Yeah, that's what the compounds are. All the ions.
Huh? How is it?
Aluminum is the stairs. So it's.
TUNGST.
I can't spell it in my life, so that's okay.
Because ClO4, chlorine is in a family of 4, and the biggest one has a couple 3, 6 parts. Because you gotta differentiate, because it's in a family of 4, there's 2 8s, so you gotta differentiate. And that's also an acid though, so perchlorate becomes what as an acid, because we ate.
Nitrite.
Is it?
Nitrite should be just the two.
That is your starting point, yes.
Oh.
So now what's the formula? It is 10-4 plus and S2 minus,
Oh, yeah, I did that cross
so you gotta cross drop and simplify. Close.
So that's what I got.
Yeah, we're gonna get it. Which won't take long. Comparatively. Maybe it's the hard part today.
So is it?
That's correct.
Oh my God. We went to Chick-fil-A and our names were Wrinkle Huff, but I accidentally put Wrinkle Huff.
Uranium's not diatomic.
That's pretty funny.
But that is awesome. Go to Starbucks and buy yourself Wrinkle Huff.
Something different every time, because we always go after chemistry, and see like
Yes,
something
that's
related to
right.
what we did.
Oh, that's funny.
It's like one week we did girls test, and we did something about organic chemistry, the next week we did, I didn't like microbes, so we did something about like big beta chemistry.
Oh. Yeah, I think Wrinkle Huff is fun to say.
It is.
So it makes it easy to memorize. This is fun to say. And a third, correct, because it's in period 2, it only has 3 options.
I've got to memorize those. We had to memorize the polytones in high school, but we didn't get threads or anything. So
Well, I tried to help with your
I feel like that would help.
I mean, you don't have to.
Someone might know something that I'm gonna try to, that seems like a more efficient way.
The right one,
Fine.
the ones on the right. It's about half a dozen one and 6 the other. I don't know. It depends on person. For me, the naming formulas on the left is easier than the one on the right. Because chemists are not very inventive, so we tend to say what we mean.
Oh.
How many chem majors do I have in here? I got one, two. Well, biochem is technically chemistry majors into biology and physics.
Yeah.
I mean, in biochemistry and physics.
So do you have 3 biochem majors?
I do apparently. I love it.
See, I don't care about the color, like the big, I don't care about, I want some myself. I like that.
I like the micro world.
Same. I don't
I
like that.
can't do the macro world.
I really know what the.
Oh, you would love working with Dr. Malden in our chemistry department. He does do a lot of fish work. Of course, he gets more into metals and the fish and stuff like that.
Yeah, I gotta find somebody soon. Let's see, we're gonna go and give you a few of the answers and see how you're doing.
The names for me. The first call, please.
Oh goodness, I better go get my charger. I'll be right back. I'm gonna go get my charger, or we may not make it. Well. The other part's easy. We'll be picking it up also, so. Maybe I can get through a few more minutes. There's half of them. Well, a fourth of them. Yes. You think you're stuck.
That's tungsten.
Right, tungsten is element 74. So it's gonna be a metal. So you need a Roman numeral, which the Roman numeral is gonna be based off the anion, basically.
Doctor, on the H, is that aqueous or gas? Or?
If I don't list it as, if I don't say aqueous, assume the other.
I will always tell you if it's an acid. I'm not as much about the other state.
Where's the map?
What's he like? He's the one who wrote the biology, like, lab book.
You just sign your teacher.
I'm just called short guys. I just put H.
So we just like, well, I mean, so like about, is it all getting like way?
All I can say is if you look at both of the cations that are polyatomic ions, they end in IUM. And if you know what ammonia is, do you know what ammonia is? Ammonia is NH3. Ammonium, therefore, would be NH4. But if you look at both ammonium and hydronium, they're both our cation polyatomics. And they both end in IUM. I don't know if that'll help.
That sounds so interesting, biochem.
So where did
That
the
sounds so
three?
interesting.
It's tough.
Is it?
It is. It depends. I won't say that it's easy, but it was actually my favorite subject. Organic chem. In fact, I'm teaching intro to organic and biochem for the nutrition majors in the spring.
So do different majors have different like levels of the same classes?
Mhm. Well, yes and no. Biology and chemistry. If you're in the College of Natural Science and Mathematics, you're going to take the full-on biochem if you take biochem. If you're in the College of Health and Behavioral Sciences, you tend to take the intro to organic and biochem if you take the biochem.
Gotcha. So they take the lesser classes, I guess.
They don't need the same level of understanding.
Gotcha.
Okay, all the answers are up there. I wanted to get them in here in case my iPad dies.
What was the rule about, when you need to put dioxide and when you can just leave it as oxide?
Oxide is only going to be used for. I'm brain thinking real quick. Oxide is only used in ionic compounds. Your covalent molecules you need to have, because they share electrons. They can have so many different possibilities. You got to specify.
Why is the second to last one right? Dioxide covers like nitrite.
Oh, very awesome question. Okay, actually, I'm glad somebody asked me this because we do need to discuss this. Because you'll see it with SO3 and O2, could be other forms. The difference, because I was asked the difference, I'll start there, is one is charged and the other is not. On the right, we have a charged ion, and we'll find out when we get to Lewis structures. We'll see the difference that charge can make. This, of course, is the polyatomic ion sulfite and nitrite. But over here, because there's no charge, that means these are covalent molecules. So the difference is it being an ion compared to being a covalent molecule. Technically, they both arise through sharing of electrons, but this has extra electrons to make it an ion. So this is sulfur trioxide. And nitrogen dioxide. And it's all because of the charge. Other questions? It's a lot. It's very doable, but it's still a lot. And in fact, on Tuesday, I will bring in flow charts because there's some questions you can ask yourself that kind of help you sort out what you're supposed to do when. Okay, because this thing's about to die, I am going to just do the rest of it on the board. We'll see how long I last. Okay, so that is the end of the naming story. Now, we're gonna pick up with something we discussed previously, and then we're going to apply that something we discussed previously to compounds. And I want another color. So back in the time frame of the first exam, we talked about how to calculate the average atomic mass for an atom of an element. It took into account all the naturally occurring isotopes of that element. And when we did the average atomic mass calculation, we were able to obtain those values that are in red on that periodic table. And what that value was for one atom of the material. We said, okay, if we have one atom of oxygen, it's going to have a mass of 15.9994 atomic mass units. But we cannot physically manipulate one atom at a time. We've only just in the last 20 years been able to start to see one atom at a time. Manipulation, not there yet. So instead of manipulating one atom at a time, we tend to talk in terms of 6.022 times 10 to the 23rd atoms. And this, when we talk about 6.022 times 10 to the 23rd, it's like a counting number. Literally, we're going 1, 2, 3, 4, 5, 6, 7, 8 until we get to 6.022 times 10 to the 23rd. Thankfully, there's machines to do that. But if we talk about 6.022 times 10 to the 23rd atoms of oxygen, now instead of talking in terms of AMUs, we can talk in terms of grams. And that is something we can easily manipulate upstairs on the balance, is grams. Now, this 6.022 times 10 to the 23rd has another name, and that is called a mole. And this is Avogadro's number. So in other words, 1 mole of oxygen would equal 15.9994 grams of oxygen. Any questions so far, or does that make perfect sense? Or relatively perfect sense? Okay.
So there's a law out there called the law of mass conservation. Mass cannot be created, nor can it be destroyed. Oxygen has its own mass. If I were to put that oxygen into carbon dioxide, for example, it has to carry its mass with it. So in carbon dioxide, we have one carbon and we have two oxygens. Each element has to carry its own mass with it. So the carbon's mass is 12.011 AMU, and the oxygen carries a mass of 15.9994 AMUs. So carbon contributes 12.011 to the overall mass, whereas oxygen contributes 31.9988 to the overall mass, making carbon dioxide's mass 44.00 or 44.0098 AMU. Now, if we talk this, we're talking about one molecule of carbon dioxide. We're talking about its formula mass. But just like our atom over here, where we could take that one atom and instead have 6.022 times 10 to the 23rd, we can instead talk about 6.022 times 10 to the 23rd molecules of carbon dioxide. And just like before, it's going to have a mass of 44.0098 grams. Now, just like this story, 6.022 times 10 to the 23rd of anything is known as 1 mole of that thing. So we can say that 44.0098 grams of oxygen is equal to 1 mole of oxygen. And now what we have is the molar mass. So the story we told back right after we started the process of creating the average atomic mass, where we talked about the fact that an atom of oxygen is in AMUs, whereas if we talk about 6.022 times 10 to the 23rd, we're now talking in terms of grams. That same exact story can be told for a molecule, because every single atom carries with it its own mass. Now, if we're talking about only one molecule, then we are talking about its formula mass. And it's got the unit of AMU, just like it had the unit of AMU. But if we're talking about 6.022 times 10 to the 23rd, now we're talking about an entire mole of the material. Oops, nobody correct me. And I did not catch myself. CO2. Now
we're talking about an entire 6.022 times 10 to the 23rd. We're talking about grams of a molecule, which is equal to a mole. And it's called its molar mass. Why is it called the molar mass? Because it has moles, mole, and it has mass, mass. And that's where I got to it this morning. I did a different compound, but I did the same process. So what we're going to be picking up with on Tuesday is I'm going to pick up with one more problem of calculating the molar mass. And then we're going to actually start using these molar masses and Avogadro's number in a conversion calculation. Then we get to move on to Lewis dot structures.